Welcome to Math Zone African Motives. Today, we're diving into a very important topic in calculus, differentiation. In this tutorial, you will be able to solve calculus problems using differentiation techniques. You'll learn to differentiate from first principles, master various differentiation rules, and understand how to find the inverse of a trigonometric function. We'll cover several key areas, from the foundational definition of the derivative to practical techniques you'll use constantly. Let's start with the very beginning, the definition of the derivative. You will be able to define the derivative of a function using first principles and understand what it represents. The derivative of a function f of x, denoted f prime of x, is defined as the limit as h approaches 0 of the expression f of x plus h minus f of x all over h. This formula might look complex, but it's the fundamental idea behind calculus. It represents the instantaneous rate of change or the slope of the tangent line to the graph of y equals f of x at any point x. In other words, it tells you how much the output of a function changes for a very, very small change in its input. We use this definition to build up all the differentiation rules. To solve this limit when h is large, let's say greater than 3, we often need a special tool called the binomial theorem. The binomial theorem is used to expand expressions like a plus b raised to a power n, which is a common occurrence in these types of problems. While this method is powerful and shows the origin of all derivatives, it can be quite lengthy. Because of this, we've developed rules to make differentiation much faster. Let's verify this goal. We have now defined the derivative from first principles. That's a crucial first step. So, since differentiating from first principles is long, we turn to techniques. These are shortcuts derived from the first principles formula. You will be able to apply the fundamental differentiation rules, including the power, product, chain, and quotient rules, to solve complex derivatives. Let's start with the most basic but incredibly powerful rule. This is the power rule. It states that the derivative of x to the power of n is equal to n times x to the power of n minus 1. A key condition here is that this rule can only be used if the exponent, n, is a constant. The rule is simple. Bring the power down as a coefficient, and then subtract 1 from the power. For example, if our function is f of x equals x to the fifth, the derivative, f prime of x, is 5 times x to the power of 5 minus 1, which simplifies to 5x to the fourth. The power rule is our first major tool for differentiation. Now we can move on to other rules that handle different scenarios, like when we have functions multiplied or divided together. What if you have two functions multiplied together? You can't just differentiate them separately. You need the product rule. The product rule is for differentiating a product of two functions, u and v. The formula is the derivative of u times v equals the derivative of u times v plus u times the derivative of v. The notation u prime and v prime simply means the derivative of u and the derivative of v, respectively. The order doesn't strictly matter because addition is commutative, but following this pattern is a good habit. Let's work through an example. Suppose f of x is the natural log of x times the quantity secant, x plus tangent x. First, let's identify u and v. We can set u equal to ln x and v equal to secant x plus tangent x. Next, we find their derivatives, u prime and v prime. The derivative of u, ln x, is 1 over x. The derivative of v, secant x plus tangent x, is secant x tangent x plus secant squared x. We can factor out a secant x. Now we plug these pieces back into the product rule formula. So f prime of x is u prime times v plus u times v prime, which gives us 1 over x times secant x plus tan x, plus ln x times secant x times tan x plus x. We can see that secant x plus tan x is a common factor, so we can factor it out to simplify our answer. The result is secant x plus tangent x, all times the quantity 1 over x plus ln x times secant. Verified using memo. We have successfully applied the product rule to solve this problem. Take a moment to see how each part, u, v, u prime, and v prime, fit together into the final answer. The chain rule is another incredibly important rule, especially for what we call composite functions. The chain rule allows us to find the derivative of a function composed of other functions. What's the difference between a product and a composite function? A product is two functions multiplied together. A composite function is when one function is inside another. For example, the natural log of secant x plus tangent x is a composite function because the sum secant x plus tangent x is the input to the natural log function. The chain rule states that the derivative of an outer function f with an inner function g inside it is the derivative of the outer function with the inner function still inside, multiplied by the derivative of the inner function. Think of it as differentiating from the outside in. Let's use the composite function we just mentioned. Let f of x equal the natural log of secant x plus tangent x. Here, the outer function, f, is ln of something, and the inner function, g, is secant x plus tangent x. So g of x equals secant x plus tangent x. Now we differentiate the outer function, the natural log. The derivative of ln of something is 1 over that something. So the derivative of the outer function, f prime of gx, is 1 over gx, which is 1 over secant x plus tangent x. But we're not done. The chain rule says we must also multiply by the derivative of the inner function. The derivative of the inner function, g prime of x, is the derivative of secant x plus tangent x, which is secant x tangent x plus secant squared x. Now we combine these two parts. F prime of x is the derivative of the outer function multiplied by the derivative of the inner function. We can simplify the second term by factoring out secant x. This gives us secant x times the quantity tangent x plus secant x, all divided by secant x plus tangent x. Notice that sec x plus tan x cancels from the numerator and denominator. So our final beautifully simplified answer is secant x, verified using memo. We have successfully applied the chain rule to solve this problem. This is a classic result you'll see frequently. The last of our core differentiation rules is the quotient rule, for when one function is divided by another. The quotient rule is used to differentiate a ratio of two functions. Let's say y equals u divided by v. Its derivative, y, is v times u prime minus u times v prime, all divided by v squared. The order of subtraction in the numerator is very important here. You can remember it as low d high minus high d low over low squared. The d stands for derivative. Let's apply this to an example. We want to find dya or dx for the function y equals 2x cubed minus 1, all divided by x squared plus 5. First, identify the top function, u, and the bottom function, v. Our u is 2x cubed minus 1, and our v is x squared plus 5. Next, find their derivatives, u prime and v prime. Using the power rule, the derivative of u is 6x squared, and the derivative of v is 2x. Now we substitute these four pieces into our quotient rule formula. So, dx equals v, x squared plus 5, times u prime 6x squared, minus u, 2x cubed minus 1 times v prime 2x. All over v squared, which is x squared plus 5 squared. Now let's expand the numerator and simplify. Distributing 6x squared gives 6x to the fourth plus 30x squared. Distributing 2x gives 4x to the fourth minus 2x. Remember to subtract the entire second term. Simplifying the numerator, we combine the like terms 6x to the fourth and minus 4x to the fourth to get 2x to the fourth. We can factor out a 2x from the numerator for a final cleaner answer. This gives us 2x times the quantity x cubed plus 15x plus 1, all over the quantity x squared plus 5 squared. Verified using memo. By carefully following the quotient rule and simplifying, we arrived at the correct derivative. So far, all the functions we've differentiated have been written as y equals f of x. We call these explicit functions. But what if y isn't isolated? That's where implicit differentiation comes in. You will be able to differentiate equations where y is not the subject, a skill essential for many applications. Consider an equation like x squared plus y squared equals 25. The graph of this is a circle, and it fails the vertical line test. For a single x, there can be two y values. So y is not a function of x, but the equation still defines a curve. Implicit differentiation allows us to find dx, the slope of the tangent line to the circle, without having to solve for y explicitly. The key rule is this. When you differentiate a term containing y with respect to x, You treat y as a function of x, so you must multiply by di with dx using the chain rule. It's the derivative of the outer function y, which is 1, times the derivative of the inner function, which is dx. Let's apply this to the circle equation. We differentiate both sides with respect to x. The derivative of x squared with respect to x is just 2x, using the power rule. Now for the y squared term. Its derivative with respect to y is 2y. But because we're differentiating with respect to x, we must multiply by di/d, so we get that 2y di/dx. So we have 2x plus 2y dix equals the derivative of 25, which is 0. Our goal is to find d/dx, so now we just solve this algebraic equation for di/eta. First, we subtract 2x from both sides. Then we divide both sides by 2y. The 2's cancel out, leaving us with dx equals negative x over y. And that's it. Notice that the slope depends on both the x and y coordinates, which makes sense for a curve like a circle. Verified using memo. This method is incredibly powerful for equations that are difficult or impossible to solve for y. Following closely on implicit differentiation is another technique that seems to make complex derivatives much easier. This is logarithmic differentiation. By the end of this scene, you will be able to simplify and differentiate complex products, quotients, and powers using logarithmic laws. Logarithmic differentiation is a clever strategy for functions with products, quotients, or powers that are complicated to differentiate using our standard rules. The core idea is to take the natural logarithm of both sides of the equation. We can take natural logarithms on both sides of an equation and then simplify using the fundamental laws of logarithms before we even think about differentiating. Let's review those laws, as they are crucial for this method. The product rule for logs lets you change a product into a sum. The quotient rule lets you change a division into a difference. And the power rule lets you bring a power down as a coefficient. These are our simplification tools. Let's work through an example that looks very intimidating. We want to find dx for y equals x cubed times the square root of x squared plus 1 divided by 1 minus 3x cubed. Imagine using the quotient rule here. You'd need the product rule for the top. It would be a huge mess. Logarithmic differentiation is perfect for this. Step 1. Take the natural log of both sides. Step 2. Simplify using the log laws. First, we use the quotient rule for logs, then the product rule, and finally the power rule on each term. Look how much simpler that expression on the right has become. Now it's easy to differentiate. Step 3. Differentiate implicitly with respect to x. The derivative of the left side, ln y, is 1 y di. Differentiating the right side, we use the chain rule for the second and third terms. The derivative is 3 over x, plus 1/2 times 2x over x squared plus 1, minus 3 times negative 3 over 1 minus 3x. Simplifying, we get 3 over x plus x over x squared plus 1 plus 9 over 1 minus 3. Finally, we need to solve for d/dx. We multiply the entire right side by y, and then we substitute back the original expression for y. This is our final answer. It looks long, but the process was systematic and much easier than trying the quotient and product rules directly. Verified using memo. Logarithmic differentiation is a powerful tool to add to your calculus toolkit. Let's shift gears slightly and talk about inverse trigonometric functions, which can also be differentiated. You will be able to understand the properties of inverse trigonometric functions and differentiate them. Think about a function like y equals sine of x. This function doesn't pass the horizontal line test. For a given y value, there are infinitely many x values. This means it doesn't have a true inverse function. However, if we restrict its domain to a specific interval, it can. This gives us the principal inverse functions like arcsin x, arccos x, and arctan x. There are a few key properties to remember about inverse functions in general. First, the graph of a function and its inverse are reflections of each other across the line y equals x. Second, to find the inverse equation, you interchange the x and y variables and then solve for the new y. This reflects the interchange of x and y coordinates for every point on the graph. Third, if the original function has a vertical asymptote, its inverse will have a corresponding horizontal asymptote. For example, The tangent function has vertical asymptotes, so its inverse arctan x has horizontal asymptotes. So we've defined what inverse trigonometric functions are. But can we differentiate them? Yes, they all have standard derivative formulas that you can find on a formula sheet. Here are the most common ones. The derivative of arcsin x is 1 over the square root of 1 minus x squared. The derivative of arccos x is the same, but negative. The derivative of arctan x is 1 over 1 plus x squared. And of course, for a composite function like arcsin of g of x, you would apply the chain rule. It would be g prime of x divided by the square root of 1 minus g of x squared. Let's see an example. Suppose we want to differentiate arcsin of x to the power of 4. Here, our inner function, g of x, is x to the fourth. The derivative of our inner function, g prime of x, is 4x cubed. Applying the chain rule, f prime of x is g prime of x divided by the square root of 1 minus g of x squared. Substituting, we get 4x cubed divided by the square root of 1 minus x to the fourth squared. Simplifying the exponent, our final answer is 4x cubed over the square root of 1 minus x to the eighth, verified using memo. We've seen how the chain rule is applied to these new types of functions. Understanding these derivatives expands the range of functions you can work with. So, let's take a moment to summarize what we've covered today. This will help you see the bigger picture of differentiation. We started with the definition of the derivative from first principles. While it's fundamental, we quickly moved to more practical differentiation techniques. We learned to apply the power, product, chain, and quotient rules. We then explored how to find derivatives of implicitly defined functions and, for complex expressions, how to use logarithmic differentiation. Finally, we touched on inverse trigonometric functions, understanding their properties and using standard formulas to find their derivatives. The most important takeaway is this: you won't always use just one rule. Very often, you'll have to use more than one rule in combination to solve a problem. For example, a quotient might have a product in the numerator, or you might need the chain rule inside a product rule. We successfully met our objectives. You should now be comfortable with these core differentiation techniques. Practice is key, so I encourage you to work through more examples. Thank you for joining Math Zone African Motives. I hope this tutorial has been helpful. If you found this video useful, please give it a thumbs up. Don't forget to subscribe to Math Zone African Motives for more step-by-step tutorials on a wide range of math topics. Hit the notification bell so you don't miss our next video. See you next time.